Torch.abs. Description. The torch.abs function calculates the absolute value of each element in a p-torch tensor. It returns a new tensor with the absolute values. Inputs. Input 1 tensor, the input tensor for which the absolute values are to be calculated. This can be any p-torch tensor, including scalars, vectors, matrices, or tensors of higher dimensions. Outputs. Output 1 tensor, a new tensor with the absolute values of the input tensor. The output tensor has the same size and data type as the input tensor. Steps. Step 1 for each element in the input tensor. The function determines its absolute value. Step 2 a new tensor is created containing the calculated absolute values. Preserving the original shape and data type. Challenges and fixes. Challenge 1 input tensor is a complex number tensor. Sample use case. Torch. Abs torch. Tensor 1 2j. 3 4j. Fixes. The function will calculate the magnitude absolute value of each complex number. Challenge 2 input tensor contains both positive and negative values. Sample use case. Torch. Abs torch. TENSOR 2. 3. -1. 5. Fixes. All negative values will be converted to their positive counterparts. Challenge 3 the input tensor contains none not a number values. Sample use case. Torch. Abs torch. Tensor float none. 2. 3. Fixes. None values will remain as none in the output tensor. Torch. Arccos. Description. The torch. Arccos function computes the inverse cosine arccosine of each element in the input tensor. It returns a new tensor with the same size as the input tensor, where each element represents the angle whose cosine is the corresponding element in the input tensor. The returned angle is in radians. Inputs. Input 1 input tensor containing the cosine values whose arccosine needs to be calculated. The input tensor should be a tensor of floating point numbers. Outputs. Output 1 a new tensor with the same size as the input tensor, containing the arccosine values of the input tensor. The output tensor will be a tensor of floating point numbers. Steps. Step 1 for each element in the input tensor. The function calculates the angle in radians whose cosine is equal to the element's value. Step 2 the function returns a new tensor with the same size as the input tensor, containing the calculated angles in radians. Challenges and fixes. Challenge 1 input tensor contains values outside the range of -1 to 1. Sample use case that resulted in challenge 1 when the input tensor contains values greater than 1 or less than -1. The function will return none not a number for those elements. Fixes to challenge 1 ensure that the input tensor contains values within the range of -1 to 1. If the input tensor contains values outside this range, you may need to adjust the values or use a different function. Challenge 2 input tensor contains complex numbers. Sample use case that resulted in challenge 2 when the input tensor contains complex numbers. The function will raise a type error. Fixes to challenge 2 ensure that the input tensor contains only real numbers. If the input tensor contains complex numbers, you may need to use a different function or extract the real part of the complex numbers before passing them to the torch. Arccos function. Torch. ACOSH. Description. The torch. ACOSH function calculates the inverse hyperbolic cosine of each element in the input tensor. In other words, it finds the angle whose hyperbolic cosine is equal to the input value. Inputs. Input 1 input. a tensor containing the values for which the inverse hyperbolic cosine will be calculated. It must be a real-valued tensor. Outputs. Output 1 output, a tensor of the same size as the input, containing the inverse hyperbolic cosine values. Steps. Step 1 for each element in the input tensor. The function calculates the inverse hyperbolic cosine using the mathematical formula a cosh ln x sqrt x2 to 1. Challenges and fixes. Challenge 1 input values less than 1. The hyperbolic cosine function has a domain of x1. If the input tensor contains values less than 1, the function will return none, not a number for those elements. Sample use case that resulted in challenge 1 input torch, tensor minus 2.0, 0.5, 1.0, 2.0. Fixes to challenge 1 ensure the input tensor contains values greater than or equal to 1. You can use clamping to achieve this input. Clampmin 1.0. Challenge 2 input values containing none or INF if the input tensor contains none, not a number, or INF infinity values. The function will return none for those elements. Sample use case that resulted in challenge 2 input torch, tensor 1.0. Floatinf. Floatnin 2.0. Fixes to challenge 2 handle or remove none and INF values before passing the input tensor to the function. Use torch, ISNA and torch, ISNF to identify these values and replace or filter them as needed. Torch, arccosh. Description. This function calculates the inverse hyperbolic cosine of each element in the input tensor. The hyperbolic cosine is defined as the inverse of the hyperbolic sine function. In other words, it returns the value whose hyperbolic cosine is equal to the input value. Inputs. Input 1 input tensor, a tensor of any shape containing the values for which the inverse hyperbolic cosine needs to be calculated. Outputs. Output 1 output tensor, a tensor of the same shape as the input tensor containing the inverse hyperbolic cosine values. Steps. Step 1 the function takes each element from the input tensor. Step 2 for each element, it calculates the value whose hyperbolic cosine is equal to the input element. This calculation is performed using the mathematical formula for the inverse hyperbolic cosine. Step 3 the calculated values are then stored in a new tensor, which is returned as the output. Challenges and fixes. Challenge 1 input values out of range. Sample use case that resulted in challenge 1 if the input tensor contains values less than 1. The function will raise an error since the hyperbolic cosine is only defined for values greater than or equal to 1. Fixes to challenge 1 to avoid this error. You can either clip the input tensor to ensure all values are greater than or equal to 1, or use the torch, clamp function to limit the input values to a specific range. Challenge 2 numerical instability for very large values. Sample use case that resulted in challenge 2 for very large input values. The numerical precision of floating point numbers can lead to instability in the computation. Fixes to challenge 2 in cases where the input values are very large. Consider using a different approach to calculate the inverse hyperbolic cosine that is less susceptible to numerical instability. For example, you might use an approximation formula or a more robust numerical algorithm. Torch.add. Description. The torch.add function in ptorch performs element-wise addition between two tensors. Inputs. Input 1 the first tensor, which can be any valid ptorch tensor. Input 2 the second tensor, which must have the same shape as the first tensor or be a scalar. Outputs. Output 1, a tensor with the same shape as the input tensors, containing the element-wise sum of the input tensors. Steps. Step 1, the function iterates through each corresponding element in the input tensors. Step 2, for each element pair, the function adds the corresponding elements together and stores the result in the corresponding element of the output tensor. Challenges and fixes. Challenge 1, input tensors must have the same shape, or one of the tensors must be a scalar. Sample use case that resulted in challenge 1, trying to add two tensors with different shapes. Fixes to challenge 1. Ensure that the input tensors have the same shape or that one of the tensors is a scalar. Use broadcasting if the input tensors have different shapes but are compatible for broadcasting. Challenge 2, input tensors must be of the same data type. Sample use case that resulted in challenge 2, trying to add a tensor of type torch float 32 to a tensor of type torch.int 32. Fixes to challenge 2. Ensure that the input tensors are of the same data type. Convert one or both of the input tensors to the desired data type using functions like torch, float or torch.int. Torch additive. Description: the torch additive function performs the element-wise addition of a tensor with a scaled and broadcasted division of two tensors. Inputs. Input 1, this is the tensor that will be added to the result of the scaled division. It can be any p-torch tensor. Input 2, this is the tensor that will be divided by the third input tensor, scaled by the second input, and added to the first input tensor. It can be any p-torch tensor. Input 3, this is the tensor that will be used to divide the second input tensor. It can be any p-torch tensor. Input 4, this is a scalar value that scales the result of the division before it is added to the first input tensor. It can be a float or a p-torch scalar tensor. Outputs. Output 1, the resulting tensor after the addition and scaling. It has the same shape as the first input tensor. Steps. Step 1, the second input tensor is divided element-wise by the third input tensor. Step 2, the result of the division is then multiplied element-wise by the fourth input, the scaling factor. Step 3, the scaled result of the division is broadcasted to match the shape of the first input tensor. Step 4, the scaled result is added element-wise to the first input tensor. Challenges and fixes. Challenge 1, the shapes of the input tensors are incompatible for broadcasting. Sample use case that resulted in challenge 1, trying to perform additive with tensors of different shapes that cannot be broadcasted together. For example, attempting to add a 2/3 tensor with a scaled division of a 1/3 tensor and a 1/1 tensor. Fixes to challenge 1, ensure the shapes of the input tensors are compatible for broadcasting. This can be achieved by either reshaping the tensors manually or by using the torch broadcast tensors function. Challenge 2, the scaling factor is not provided or is invalid. Sample use case that resulted in challenge 2, calling additive without specifying a scaling factor, or providing a value that is not a scalar. Fixes to challenge 2, provide a valid scaling factor as the fourth input argument to the additive function. The scaling factor should be a scalar value, which can be a float or a p-torch scalar tensor. Challenge 3, division by 0 is encountered. Sample use case that resulted in challenge 3, the third input tensor contains 0 values, leading to division by 0. Fixes to challenge 3, handle division by 0 by either avoiding it in the input tensors or by using a conditional statement to check for 0 values and replace them with a very small value before performing the division. Torch additive. Description: the torch ADMSOL function performs the following operation. Out input value tensor 1 tensor 2. Where input the input tensor value the scalar value to multiply with the product of tensor 1 and tensor 2. Tensor 1 the first tensor to be multiplied with tensor 2. Tensor 2 the second tensor to be multiplied with tensor 1. This function is equivalent to out input value torch mul tensor 1. Tensor 2. But it is more efficient for large tensors. Inputs. Input the input tensor. It can be any tensor supported by p-torch. Value a scalar value to be multiplied with the product of tensor 1 and tensor 2. It must be a scalar. Tensor 1 the first tensor to be multiplied with tensor 2. It must have the same dimensions as tensor 2 if broadcasting is not enabled. Tensor 2 the second tensor to be multiplied with tensor 1. It must have the same dimensions as tensor 1 if broadcasting is not enabled. Outputs. Out the output tensor. It will have the same dimensions as the input tensor. Steps. Multiply tensor 1 and tensor 2 element-wise. Multiply the result from the previous step by value. Add the result from the previous step to the input tensor. Challenges and fixes. Challenge 1 broadcasting error when tensors have different dimensions. Broadcasting is applied to align the tensors before multiplication. If broadcasting is not possible, it will result in an error. Sample use case that resulted in challenge 1 torch, ADMSOL torch, tensor 1. 2, 3, 2, torch, tensor 1, 2, torch, tensor 1, 2, 3. Fixes to challenge 1 ensure that the tensors have compatible dimensions for broadcasting. You can use the torch, broadcast tensors function to check for broadcast compatibility. Challenge 2 data type mismatch. The tensors and the scalar value should have compatible data types. If the data types are not compatible, it will result in an error. Sample use case that resulted in challenge 2 torch, ADMSOL torch, tensor 1, 2, 3, D-type torch, float 32, 2, torch, tensor 1, 2, torch, tensor 1, 2, 3, D-type torch.int 64. Fixes to challenge 2 ensure that the data types of the tensors and the scalar value are compatible. You can use the torch, tensor function with the D-type argument to specify the desired data type. Torch, ascene. Description. The torch, ascene function calculates the element-wise inverse sine arcsine of a tensor. It returns a new tensor with the same shape as the input tensor, containing the arcsine values of each element. Inputs. Input 1 input tensor, a tensor containing the values for which to calculate the arcsine. The elements of the input tensor must be within the range -1. 1. Outputs. Output 1 output tensor, a tensor containing the arcsine values of the input tensor elements. The output tensor has the same shape as the input tensor and contains values in the range pi2. Pi2. Steps. Step 1 the function iterates through each element of the input tensor. Step 2 for each element, it calculates the inverse sine using the mathematical arcsine function. Step 3 the calculated arcsine value is stored in the corresponding element of the output tensor. Challenges and fixes. Challenge 1 input values outside the range -1. 1. Sample use case that resulted in challenge 1 torch, ascene torch, tensor 2.0. Fixes to challenge 1 the function raises a runtime error if any element in the input tensor is outside the range -1. 1. Challenge 2 input tensor with complex numbers. Sample use case that resulted in challenge 2 torch, ascene torch, tensor 1.1j. Fixes to challenge 2 the function currently does not support complex numbers. If the input tensor contains complex numbers, it will raise a runtime error. Torch, arcsine. Description computes the element-wise inverse sine arcsine of the given input tensor. Input a tensor containing the values for which to calculate the arcsine. Output a tensor with the same shape as the input, containing the arcsine of each element in the input tensor. The output values are in radians. The function iterates through each element in the input tensor. For each element, it calculates the inverse sine using the underlying math library. The result is stored in the corresponding position in the output tensor. Challenge 1 input values outside the range -1. 1. The arcsine function is only defined for values between -1 and 1. If the input contains values outside this range, the function will raise an error. Sample use case torch, arcsine torch, tensor 2.0. Fixes to challenge 1 ensure that the input tensor contains values within the range -1. 1. Before calling the function, you can clamp the input values using torch, clamp to restrict them to the desired range. Challenge 2 numerical instability for values very close to -1 or 1. The arcsine function can become numerically unstable, leading to inaccurate results. Sample use case torch, arcsine torch, tensor 0.99999999999999. Fixes to challenge 2 use a more robust numerical method for calculating the arcsine for values near the boundaries of the domain. Torch, ASIN. Description. The torch, ASIN function computes the inverse hyperbolic sine arcsine of each element in the input tensor. It returns a new tensor with the same size as the input tensor, where each element is the inverse hyperbolic sine of the corresponding element in the input tensor. Inputs. Input 1. Input a tensor containing numbers for which to compute the inverse hyperbolic sine. Outputs. Output 1. A tensor containing the inverse hyperbolic sine of each element in the input tensor. Steps. Step 1. The function calculates the inverse hyperbolic sine of each element in the input tensor. Challenges and fixes. Challenge 1. Input tensor has invalid data type. Sample use case that resulted in challenge 1. A user attempts to compute the inverse hyperbolic sine of a tensor with a data type that is not supported by the torch, ASIN function, such as a string tensor. Fixes to challenge 1. Ensure that the input tensor is of a supported data type, such as a float or double tensor. Challenge 2. Input tensor contains none or infinity values. Sample use case that resulted in challenge 2. A user attempts to compute the inverse hyperbolic sine of a tensor that contains none or infinity values. Fixes to challenge 2. Handle none and infinity values appropriately, either by replacing them with valid values or by masking them out. Torch, arcsine. Description. The torch, arcsine function computes the inverse hyperbolic sine of the input tensor element-wise. It is also known as the area hyperbolic sine function. Inputs. Input a tensor of any shape containing the input values for which the inverse hyperbolic sine needs to be calculated. It can be of any data type that supports mathematical operations. Outputs. Output a tensor with the same shape as the input tensor. Each element in the output tensor represents the inverse hyperbolic sine of the corresponding element in the input tensor. The output tensor will have the same data type as the input tensor. Steps. The function iterates through each element of the input tensor. For each element, it calculates the inverse hyperbolic sine using the mathematical formula arcsine hx ln x sqrtx21. The calculated value is stored in the corresponding element of the output tensor. Challenges and fixes. Challenge 1. The input tensor might contain values that are not within the domain of the arcsign function, such as nan not a number or inf infinity. Sample use case that resulted in challenge 1. Input tensor torch. Tensor float n f. Float n. 1.0. Fixes to challenge 1. The torch arcsign function handles these cases gracefully. It returns nan for nan inputs and inf for inf inputs. Challenge 2. The input tensor might contain values that are very large or very small, which could lead to numerical instability during the calculation. Sample use case that resulted in challenge 2. Input tensor torch. Tensor 1e30. 1e30. Fixes to challenge 2. The torch arcsign function is implemented with numerical stability in mind, and typically handles such cases appropriately. However, if you encounter instability issues, you might consider scaling the input tensor before applying the function. Torch arctan. Description. The torch arctan function calculates the element-wise arctangent inverse tangent of a input tensor. The arctangent is the angle whose tangent is the input value, expressed in radians. Inputs. Input 1. Input, a tensor of any shape containing the values for which to calculate the arctangent. The data type of the input tensor can be any of the supported numerical data types in ptorch, such as torch, float 32, torch, float 64, torch.int 32, etc. Outputs. Output 1. Output, a tensor of the same shape as the input tensor, containing the element-wise arctangent of the input values. The data type of the output tensor will be the same as the input tensor. Steps. Step 1. For each element in the input tensor, torch arctan calculates the arctangent using the mathematical formula arctanx. Challenges and fixes. Challenge 1. Input tensor with invalid data type. The torch arctan function only accepts numerical input tensors. If the input tensor contains non-numerical data, the function will raise a type error. Sample use case that resulted in challenge 1. Input torch tensor 1. 2. ABC. Fixes to challenge 1. Convert the input tensor to a valid numerical data type before passing it to torch arctan. For example, input torch tensor 1. 2. ABC. D-type torch float 32. Challenge 2. Input tensor with values that are not defined for arctangent. The arctangent function is only defined for real numbers. If the input tensor contains complex numbers or infinite values, the function will raise a value error. Sample use case that resulted in challenge 2. Input torch tensor float n f. Float env 1j. Fixes to challenge 2. Ensure that the input tensor contains only real numbers that are defined for the arctangent function. For example, input torch tensor 1.0, 2.0, 3.0. Torch ATANH. Description. The torch ATANH function calculates the inverse hyperbolic tangent of each element in the input tensor. In simpler terms, it returns the angle whose hyperbolic tangent is equal to the input. Inputs. Input 1. Input tensor. The input tensor must be a real-valued tensor. Outputs. Output 1. Output tensor, a tensor with the same size as input, containing the inverse hyperbolic tangent of each element in the input tensor. Steps. Step 1. The function takes an input tensor. Step 2. It calculates the inverse hyperbolic tangent of each element in the tensor using the Formula ATANHX12 ln 1 by 1x. Challenges and fixes. Challenge 1. The input tensor must contain values within the range of -1 to 1, excluding -1 and 1. Sample use case that resulted in challenge 1. If you attempt to calculate the inverse hyperbolic tangent of a value outside this range, the function will return none, not a number. Fixes to challenge 1. Ensure that the input tensor contains values within the valid range before applying the torch ATANH function. You can use a clam operation to limit the input tensor's values to within the acceptable range. Challenge 2. While the torch ATANH function can handle tensors of different data types, it's crucial to ensure that the input tensor's data type is appropriate for accurate results. Sample use case that resulted in challenge 2. If you input a tensor with an incompatible data type, the function might produce inaccurate results or errors. Fixes to challenge 2. Make sure the input tensor's data type is compatible with the torch ATANH function. You can use the torch.to function to convert the input tensor to a suitable data type like torch, float or torch, double. Torch, arctan. Description. The torch, arctan function computes the inverse hyperbolic tangent of each element in the input tensor. This function is also known as the hyperbolic arctangent or the area hyperbolic tangent. Inputs. Input a tensor containing the values whose inverse hyperbolic tangent needs to be computed. The input tensor can be of any shape and data type. Outputs. Output a tensor of the same shape as the input tensor, containing the inverse hyperbolic tangent values of the input elements. The output tensor will have the same data type as the input tensor. Steps. The function calculates the inverse hyperbolic tangent of each element in the input tensor. Challenges and fixes. Challenge 1. Input tensor contains values outside the range of -1. 1. Sample use case that resulted in challenge 1. If the input tensor contains values greater than 1 or less than -1, the function will return none, not a number for those elements. Fixes to challenge 1. Clam the input tensor to the range of -1. 1 before applying the arctan function. This ensures that the function only operates on valid values and avoids producing non-outputs. Challenge 2. Input tensor contains values close to 1 or -1. Sample use case that resulted in challenge 2. Values very close to 1 or -1 can lead to numerical instability and result in inaccurate or imprecise outputs. Fixes to challenge 2. Use the torch ATANH function instead of the torch arctan function when dealing with values close to 1 or -1. The torch ATANH function is more numerically stable and provides more accurate results for values near the edges of the domain. Torch ATM2. Description. The torch ATM2 function calculates the element-wise arctangent of the given input tensors, which represents the angle in radians between the x-axis and the line connecting the origin to the point y, x. It is useful for converting rectangular coordinates x, y to polar coordinates radius, angle, or for determining the angle between two vectors. Inputs. Input 1 y, a tensor of values representing the y coordinates of the points. Input 2 x, a tensor of values representing the x coordinates of the points. Outputs. Output 1, a tensor containing the arctangent of yx in the range of pi. Steps. Step 1. For each element in the input tensors, the function calculates the ratio of the corresponding y and x values. Step 2. The arctangent ATM function is then applied to this ratio. resulting in the angle in radians. Challenges and fixes. Challenge 1, division by 0 when the x-coordinate is 0. The ratio yx becomes undefined. Sample use case that resulted in challenge 1. Torch, atom 2 torch, tensor 1.0. Torch, tensor 0.0. Fixes to challenge 1. The function handles this case by returning pi2 if y is positive and pi2 if y is negative. Challenge 2, none or INF values in input tensors if either the y or x coordinates contain none or INF values. The resulting angle will also be none or INF. Sample use case that resulted in challenge 2. Torch, atom 2 torch, tensor float and f. Torch, tensor 1.0. Fixes to challenge 2. The function propagates these values as is, as they indicate undefined or infinite angles. Torch, arctan 2. Description. This function computes the element-wise arctangent of the given input tensors. It returns the angle in radians between the x-axis and the line connecting the origin to the point x. Y. Inputs. Input 1, the y-coordinate of the point. It can be a tensor of any shape. Input 2, the x-coordinate of the point. It should have the same shape as input 1. Outputs. Output, the element-wise arctangent of the input tensors. It has the same shape as input 1 and input 2. The angle is returned in the range pi. Pi. Steps. For each element in the input tensors, the function computes the arctangent of yx, where y is the corresponding element in input 1 and x is the corresponding element in input 2. The result is then scaled to the range pi. Pi based on the signs of x and y. Challenges and fixes. Challenge 1, division by 0. Sample use case that resulted in challenge 1 when the x-coordinate input 2 is 0. The division by 0 error occurs. Fixes to challenge 1. The function handles this case by setting the output to pi2 or pi2 depending on the sign of y. Challenge 2, handling non-inputs. Sample use case that resulted in challenge 2 if either input 1 or input 2 contains non-values. The output will also contain non-values. Fixes to challenge 2. The function propagates non-values. If either input 1 or input 2 contains none, the corresponding output element will be none. Torch, bitwise NOT. Description performs a bitwise NOT operation on the input tensor. This operation flips the bits of each element in the tensor. Inputs. Input 1, a tensor containing the values on which the bitwise NOT operation will be performed. The input tensor can be of any data type. Outputs. Output 1, a tensor with the same size and data type as the input tensor, containing the results of the bitwise NOT operation. Steps. Step 1, the function iterates through each element in the input tensor. Step 2, for each element, it performs a bitwise NOT operation, which flips the bits of the element. Step 3, the result of the bitwise NOT operation is stored in the corresponding element of a output tensor. Challenges and fixes. Challenge 1, the input tensor must be of a data type that supports bitwise operations. Sample use case that resulted in challenge 1 using a tensor of floating point numbers as input. Fixes to challenge 1 convert the input tensor to an integer data type before performing a bitwise NOT operation. Challenge 2, the output tensor will have the same size and data type as the input tensor. Sample use case that resulted in challenge 2 performing the bitwise NOT operation on a tensor with a specific size and data type. Fixes to challenge 2, the output tensor will have the same size and data type as the input tensor. No fix required. Torch, bitwise and description. This function performs a bitwise AND operation on two tensors. Element-wise. Inputs. Input 1, a tensor of any supported data type. The elements of this tensor will be used as the first operand for the bitwise AND operation. Input 2, a tensor of the same data type as input 1. The elements of this tensor will be used as the second operand for the bitwise AND operation. Outputs. Output 1, a tensor of the same size and data type as input 1 and input 2. Containing the results of the bitwise AND operation between corresponding elements of input 1 and input 2. Steps. The function iterates over the corresponding elements of input 1 and input 2. For each pair of elements, it performs a bitwise AND operation. The result of each bitwise AND operation is stored in the corresponding element of the output. Tensor. Challenges and fixes. Challenge 1, the inputs must be tensors of the same data type. Sample use case that resulted in challenge 1. Trying to perform a bitwise AND operation between two tensors of different data types, such as a tensor of integers and a tensor of floats. Fixes to challenge 1. Convert both tensors to the same data type before performing the bitwise AND operation. Use a tensor of a data type that supports bitwise operations, such as integers. Challenge 2, the inputs must have the same size. Sample use case that resulted in challenge 2. Trying to perform a bitwise AND operation between two tensors of different sizes. Fixes to challenge 2. Broadcast the smaller tensor to match the size of the larger tensor. Use the torch broadcast tensors function to broadcast the tensors before performing the bitwise AND operation. Torch bitwiso. Description: the torch bitwiso function performs a bitwise OR operation on two tensors. Element-wise. The result for each element is 1 if at least one of the corresponding bits in the input tensors is 1. Otherwise, the result is 0. Inputs. Input 1, a tensor containing integer values. Input 2, another tensor containing integer values. The size of the input tensors must be compatible for broadcasting. Outputs. Output 1, a tensor containing the result of the bitwise OR operation. The size and data type of the output tensor match the input tensor with the larger size. Steps. Step 1, the torch bitwiso function iterates through each element of the input tensors, comparing the corresponding bits in the two tensors. Step 2, for each element, if at least one of the corresponding bits is 1, the output element is set to 1. Otherwise, the output element is set to 0. Challenges and fixes. Challenge 1, input tensors with incompatible shapes. The shapes of the input tensors must be compatible for broadcasting. Sample use case that resulted in challenge 1, torch bitwise or torch tensor 1, 2, 3, torch tensor 4, 5. Fixes to challenge 1: ensure the input tensors have compatible shapes by either reshaping or expanding the dimensions of one or both tensors to match the other. Challenge 2: input tensors with different data types. The input tensors should have compatible data types. Sample use case that resulted in challenge 2, torch bitwise or torch tensor 1, 2, 3. D-type torch.int64. Torch tensor 4, 5. D-type torch float 32. Fixes to challenge 2: cast both input tensors to a compatible data type before performing a bitwise OR operation. Torch bitwise XOR. Description: the torch bitwise XOR function performs the bitwise XOR operation on two tensors. Element-wise. Inputs. Input 1, a tensor containing integer values, e.g. torch tensor 1, 2, 3. Input 2 another tensor containing integer values having the same shape as input 1, e.g. torch, tensor 4, 5, 6. Outputs. Output 1 a tensor with the same shape as the input tensors, containing the result of the bitwise XOR operation for each corresponding element. Steps. Step 1 the function iterates through each element of the input tensors. Step 2 for each corresponding pair of elements, it performs the bitwise XOR operation, producing a new element for the output tensor. Challenges and fixes. Challenge 1 using tensors with incompatible shapes. Sample use case that resulted in challenge 1 torch, bitwise XOR torch, tensor 1, 2, 3, torch, tensor 4, 5. Fixes to challenge 1 ensure both input tensors have the same shape. Challenge 2 using tensors containing non-integer values. Sample use case that resulted in challenge 2 torch, bitwise XOR torch, tensor 1.0, 2.0, 3.0, torch, tensor 4.0, 5.0, 6.0. Fixes to challenge 2 use tensors containing integer values. Challenge 3 using tensors with different data types. Sample use case that resulted in challenge 3 torch, bitwise XOR torch, tensor 1, 2, 3, dtype torch.int32, torch, tensor 4, 5, 6, dtype torch.int64. Fixes to challenge 3 ensure both input tensors have the same data type. Torch bitwise left shift. Description performs a bitwise left shift operation on two tensors. Inputs. Input 1 the first input tensor. It represents the value to be shifted. Input 2 the second input tensor. It represents the number of positions to shift. This input is often an integer tensor. Outputs. Output 1 a tensor of the same size as the input tensor. Each element of the output tensor is the result of shifting the corresponding element in the input tensor left by the number of positions specified by the corresponding element in the second input tensor. Steps. For each element in the first input tensor, the operation shifts the bits of the element to the left by the number of positions specified in the corresponding element of the second input tensor. Zeros are filled in the positions that are vacated by the shift. Challenges and fixes. Challenge 1 incorrect input types. Sample use case providing non-integer inputs for the second input tensor. Fixes to challenge 1 ensure that both inputs are integer tensors, either int or long types. For proper bitwise operations. Challenge 2 overflowing shift values. Sample use case shifting a value by a number of positions larger than the bit length of the data type. Fixes to challenge 2 if the shift value is too large. It can lead to unexpected results due to overflow. To prevent this, make sure the shift value is within the acceptable range for the data type. For instance, a shift value exceeding 31 for a 32-bit integer could result in an unexpected outcome. Torch bitwise right shift. Description: the torch bitwise right shift function performs a bitwise right shift operation on two input tensors. It shifts the bits of the first input tensor to the right by the number of positions specified in the second input tensor. Inputs. Input 1 the first input tensor, which is the value to be shifted. It can be an integer or a tensor containing integers. Input 2 the second input tensor, which specifies the number of positions to shift the bits to the right. It must be an integer or a tensor containing integers. Outputs. Output 1 a tensor containing the result of the bitwise right shift operation. Steps. Step 1. The function first converts both input tensors to integers. Step 2. It then performs the bitwise right shift operation on each element of the first input tensor, shifting the bits to the right by the number of positions specified in the corresponding element of the second input tensor. Step 3. The function returns a tensor containing the results of the bitwise right shift operation. Challenges and fixes. Challenge 1. If the second input tensor is negative, the result is undefined. Sample use case that resulted in challenge 1. Torch. Bitwise right shift torch. Tensor 10. Torch. TENSOR 2. Fixes to challenge 1. To avoid undefined behavior, ensure the second input tensor is always non-negative. Challenge 2. If the second input tensor is larger than the number of bits in the first input tensor, the result will be 0. Sample use case that resulted in challenge 2. Torch. Bitwise right shift torch. Tensor 10. Torch. Tensor 10. Fixes to challenge 2. Ensure that the second input tensor is smaller than the number of bits in the first input tensor, or use a modulo operation to ensure that the shift amount is within the valid range. Challenge 3. If the first input tensor contains floating point values, the function will raise an error. Sample use case that resulted in challenge 3. Torch. Bitwise right shift torch. Tensor 1.0. Torch. Tensor 2. Fixes to challenge 3. Ensure that the first input tensor contains only integer values. Challenge 4. If the input tensors are not of the same size, the function will raise an error. Sample use case that resulted in challenge 4. Torch. Bitwise right shift torch. Tensor 10. Torch. Tensor 1, 2, 3. Fixes to challenge 4. Ensure that the input tensors are of the same size. Challenge 5. If the second input tensor contains non-integer values, the function will raise an error. Sample use case that resulted in challenge 5. Torch. Bitwise right shift torch. Tensor 10. Torch. Tensor 1.5. Fixes to challenge 5. Ensure that the second input tensor contains only integer values. Torch. Ceil. Description. The torch, ceil function is a mathematical operation that rounds each element of an input tensor to the smallest integer greater than or equal to that element. This is also known as the ceiling function. Inputs. Input 1. Input, a tensor of any shape containing numeric values. Outputs. Output 1. A tensor with the same shape as the input tensor, containing the rounded up values. Steps. Step 1. For each element in the input tensor, it determines the smallest integer greater than or equal to that element. Step 2. It creates a new tensor with the same shape as the input tensor and populates it with the calculated rounded up values. Challenges and fixes. Challenge 1. Handling non-values. If the input tensor contains non-values, the output tensor will also contain non-values at the corresponding positions. Sample use case that resulted in challenge 1. If the input tensor is 1.5, 2.3, non, 3.8, the output tensor will be 2.0, 3.0, non, 4.0. Fixes to challenge 1. To handle non-values, you can use a conditional statement to check for non-values and replace them with the desired value, e.g., 0 or another value before applying the ceil function. Challenge 2. Handling complex numbers. The ceil function is not defined for complex numbers. Sample use case that resulted in challenge 2. If the input tensor contains complex numbers, the ceil function will raise an error. Fixes to challenge 2. To handle complex numbers, you can separate the real and imaginary parts of the complex numbers and apply the ceil function separately to the real parts. Torch. Clam. Description. The torch clam function is used to limit the values of a tensor within a specified range. It takes a tensor as input and returns a new tensor with the values clamped within the specified minimum and maximum values. Inputs. Input 1 input tensor, the tensor whose values are to be clamped. Input 2 minutes, the minimum value to clamp the tensor. Input 3 max, the maximum value to clamp the tensor. Outputs. Output 1 clamped tensor, a tensor with the same shape as the input tensor, but with all values clamped within the specified range. Steps. Step 1 iterate through each element of the input tensor. Step 2 if the element is less than the minimum value, set it to the minimum value. Step 3 if the element is greater than the maximum value, set it to the maximum value. Step 4 return the modified tensor. Challenges and fixes. Challenge 1 input tensor is not a valid tensor. Sample use case that resulted in challenge 1 passing a non-tensor object as input. Fixes to challenge 1 ensure the input is a valid p-torch tensor. Challenge 2 minimum value is greater than the maximum value. Sample use case that resulted in challenge 2 calling torch clam with min 10 and max 5. Fixes to challenge 2 ensure the minimum value is less than or equal to the maximum value. Challenge 3 input tensor has a dimension that is not supported by the function. Sample use case that resulted in challenge 3 calling torch clam on a tensor with more than 4 dimensions. Fixes to challenge 3 ensure the input tensor has a supported number of dimensions. Torch.max. Description. The torch.max function is used to find the maximum values along a specified dimension. In a tensor, it returns a tuple containing the maximum values and their indices. Inputs. Input 1 input, the input tensor. Input 2 dim optional, the dimension to reduce. By default, the maximum value is computed across the flattened tensor. Outputs. Output 1 values, a tensor containing the maximum values. The shape of this tensor is the same as the input tensor, except for the dimension that was reduced. Output 2 indices, a tensor containing the indices of the maximum values. The shape of this tensor is the same as the input tensor, except for the dimension that was reduced. Steps. Step 1 the function iterates through the specified dimension in the input tensor. Step 2 for each element in the dimension, it compares the value with the current maximum value. If the element is greater, it updates the maximum value in its index. Challenges and fixes. Challenge 1 when dim is not specified, the maximum value is computed across the flattened tensor. This might not be desirable if the input tensor has multiple dimensions. Sample use case that resulted in challenge 1 a user wants to find the maximum value along a specific dimension in a multi-dimensional tensor, but they forget to specify the dim argument. Fixes to challenge 1 specify the dim argument to compute the maximum value along the desired dimension. Challenge 2 the indices tensor returned by torch.max might not be the same shape as the input tensor if the dim argument is specified. Sample use case that resulted in challenge 2 a user is expecting the indices tensor to have a same shape as the input tensor, but the dim argument is specified. Fixes to challenge 2 use the keep dim argument to ensure that the indices tensor has the same shape as the input tensor. Torch clip. Description clip. Contrastive language image pre-training is a powerful technique for aligning text and image representations in a joint embedding space. p-torch clip is a library that provides pre-trained clip models and tools for performing various tasks, such as image classification, image captioning, and text image retrieval. Inputs. Text. This is the textual input, such as a sentence, phrase, or even a single word. It is typically encoded using a text encoder, e.g., a transformer model. Image. This is the image input, typically represented as a tensor of pixel values. It is encoded using an image encoder, e.g., a convolutional neural network. Outputs. Text embeddings. These are numerical representations of the input text, capturing its semantic meaning. Image embeddings. These are numerical representations of the input image, capturing its visual features. Steps. Encoding. Both the text and image inputs are fed through their respective encoders, resulting in text and image embeddings. Alignment. The text and image embeddings are projected into a common embedding space, where they are compared using a contrastive loss function. The goal is to minimize the distance between embeddings of related text-image pairs and maximize the distance between embeddings of unrelated pairs. Fine-tuning optional. The pre-trained CLIP model can be fine-tuned on a specific downstream task, such as image classification or text-image retrieval, by adjusting the model's weights to optimize performance on that task. Challenges and fixes. Challenge 1. Out-of-memory errors. This can occur when processing large images or when using very large models. Sample use case. Trying to process high-resolution images on a device with limited memory. Fixes. Reduce image size. Resizing images to a smaller resolution can significantly reduce memory usage. Use a smaller model. Experimenting with smaller CLIP models, e.g., Wit-base, can decrease memory requirements. Utilize GPU. Using a GPU with sufficient memory can handle larger images and models. Optimize data loading. Adjusting data loading parameters, e.g., batch size, number of workers, can help manage memory usage. Challenge 2. Slow inference times. Large CLIP models can be computationally expensive, leading to slower inference speeds. Sample use case. Processing many images in real time for a live application. Fixes. Reduce model size. Consider using a smaller CLIP model for faster processing. Quantization. Quantizing the model's weights to lower precision, e.g., 8-bit, can significantly improve inference speed. Hardware acceleration. Leveraging specialized hardware, e.g., TPUs, GPUs, can significantly speed up inference. Optimize code. Profiling the code and optimizing critical sections can improve efficiency. Challenge 3. Limited domain knowledge. Pre-trained CLIP models are trained on a vast dataset but may not generalize well to specific domains, such as medical images or satellite imagery. Sample use case. Using CLIP for image classification in a medical context. Fixes. Fine-tuning. Fine-tuning the pre-trained CLIP model on a domain-specific dataset can improve its performance. Domain-specific encoders. Consider using domain-specific image encoders trained on relevant data. Data augmentation. Augmenting the training data with domain-specific examples can help the model generalize better. Challenge 4. Bias and fairness. Pre-trained CLIP models can exhibit biases inherited from training data. Sample use case. CLIP may assign different scores to images of people from different ethnicities or genders. Fixes. Bias detection. Identify and quantify bias in the model's output through various methods, such as analyzing the model's predictions on specific data subsets. The biasing techniques employ methods to reduce or mitigate bias, such as adversarial training or bias mitigation techniques. Diversity in training data. Ensure the training data is diverse and representative of the real world. Challenge 5. Textual prompt engineering. The quality of the text input significantly impacts the performance of CLIP. Sample use case. Using vague or poorly constructed prompts can lead to inaccurate results. Fixes. Clear and specific prompts. Craft prompts that are clear, concise, and directly related to the desired outcome. Experiment with different prompts. Try variations of the prompt to see which yields the best results. Use prompt engineering techniques. Employ prompt engineering techniques to improve performance of clip, such as adding context or using specific keywords. YAML. Torch Conj Physical. Description. The torch Conj physical function computes the element-wise complex conjugate of a tensor, taking into account the physical meaning of the input. Inputs. Input 1 AP torch tensor representing a complex valued quantity. Outputs. Output 1 AP torch tensor with the same shape and data type as the input, containing the complex conjugate of the input tensor. Steps. Step 1 for each element in the input tensor. The torch Conj physical function performs the following. If the input element is a complex number, it swaps the signs of the imaginary part. If the input element is a real number, it returns the same element without any modification. Challenges and fixes. Challenge 1. When dealing with tensors that have a complex data type but contain only real numbers, torch Conj physical might not have a noticeable effect. Sample use case that resulted in challenge 1. Creating a complex tensor using torch complex real tensor. Torch zeros like real tensor, where real tensor is a real valued tensor. Fixes to challenge 1. If the input tensor is known to contain only real numbers, it is recommended to use a different function for computing the conjugate, such as torch Conj. Challenge 2. If the input tensor is not a complex valued tensor, torch Conj physical might raise an error. Sample use case that resulted in challenge 2. Using a tensor with a data type other than complex, such as torch float32 or torch.int64, as input to torch Conj physical. Fixes to challenge 2. Ensure that the input tensor has a complex data type, such as torch complex 64 or torch complex 128. Torch copy sign. Description. The torch copy sign function copies the sign of one input tensor to another input tensor. It returns a new tensor with the magnitude of the first input tensor and the sign of the second input tensor. Inputs. Input a tensor of any shape. This represents the magnitude of the output tensor. Other a tensor of any shape. This represents the sign of the output tensor. The other tensor must have the same d-type and shape as the input tensor. Outputs. Output a tensor with the same shape and d-type as the input tensor. This tensor has the magnitude of the input tensor and the sign of the other tensor. Steps. The torch copy sign function first checks if the input and other tensors have the same d-type and shape. If not, it raises an error. The function then iterates over the elements of the input and other tensors. For each element, the function checks the sign of the corresponding element in the other tensor. If the sign of the other element is positive, the function keeps the original value of the input element. If the sign of the other element is negative, the function negates the original value of the input element. The function returns a new tensor with the updated values. Challenges and fixes. Challenge 1. The input and other tensors must have the same d-type and shape. Sample use case that resulted in challenge 1. Torch copy sign torch tensor 1.0, 2.0, 3.0. Torch tensor 1.0, 2.0. Fixes to challenge 1. Ensure that the input and other tensors have the same d-type and shape before calling the torch copy sign function. Challenge 2. The other tensor must have the same d-type as the input tensor. Sample use case that resulted in challenge 2. Torch Copy sign torch, tensor 1.0, 2.0, 3.0, torch, tensor 1, 2, 3, fixes to challenge 2. Convert the other tensor to the same D-type as the input tensor before calling the torch, copy sign function. Torch.cos. Description. The torch.cos function calculates the cosine of each element in a p-torch tensor. It operates on tensors containing numerical data, such as floating point numbers. The cosine function is a trigonometric function that relates an angle to the ratio of the adjacent side to the hypotenuse in a right triangle. Inputs. Input 1 input, a p-torch tensor containing numerical data. Outputs. Output 1 a p-torch tensor with the same shape as the input tensor. Each element in the output tensor represents the cosine of the corresponding element in the input tensor. Steps. Step 1 for each element in the input tensor. The function calculates the cosine value using the mathematical formula for cosine. Challenges and fixes. Challenge 1 input tensor contains non-numerical data. The torch.cos function expects numerical data as input. If the input tensor contains non-numerical data, like strings or booleans, it will raise an error. Sample use case that resulted in challenge 1 torch, cos torch, tensor hello. 1.0. Fixes to challenge 1 ensure that the input tensor contains only numerical data. Convert non-numerical data to numerical data using appropriate methods before applying torch.cos. Challenge 2 input tensor has a complex data type. The torch.cos function is designed to work with real-valued tensors. If the input tensor has a complex data type, it will raise an error. Sample use case that resulted in challenge 2 torch, cos torch, tensor 1.02.0j. Fixes to challenge 2 ensure that the input tensor has a real-valued data type. If necessary, convert complex data to real data using methods like torch, real or torch, IMAG. Torch, cosh. Description. The torch, cosh function calculates the hyperbolic cosine of each element in the input tensor. It is defined as expx express x2, where x is the input tensor. Inputs. Input a tensor containing the values for which to calculate the hyperbolic cosine. The input can be any data type supported by p-torch. Outputs. Output a tensor with the same shape and data type as the input tensor, containing the hyperbolic cosine of each element in the input. Steps. The function iterates over each element in the input tensor. For each element, it calculates expx and express x, where x is the current element. It then calculates the hyperbolic cosine using the formula expx express x2. The calculated hyperbolic cosine is stored in the corresponding element of the output tensor. Challenges and fixes. Challenge 1 non-values. Sample use case that resulted in challenge 1 if the input tensor contains extremely large values. The calculation of expx and express x might result in not a number values due to the limitations of floating point precision. Fixes to challenge 1 use a different numerical method for calculating the hyperbolic cosine, such as using the Taylor series approximation, which is more robust to large input values. Challenge 2 overflow. Sample use case that resulted in challenge 2 if the input tensor contains extremely large values. The calculation of expx and express x might result in an overflow error, as the values exceed the maximum representable value for the data type. Fixes to challenge 2 use a data type with a larger range, such as float 64. to accommodate the larger values. You can also consider rescaling the input values before applying the hyperbolic cosine function. Torch.dev. Description. The torch.dev function performs element-wise division of two tensors. It is a versatile function that can handle various division scenarios, including integer division and floating point division. It also supports different rounding modes for integer division. Inputs. Input 1, a tensor representing the dividend. Input 2, a tensor representing the divisor. The shapes of the two input tensors must be broadcastable. Outputs. Output 1, a tensor containing the element-wise results of the division. The shape of the output tensor is determined by the broadcasting rules. Steps. Step 1, broadcasting. If the input tensors have different shapes, the torch.dev function first broadcasts them to a common shape. Step 2, division. The function then performs element-wise division between the corresponding elements of the broadcasted input tensors. Challenges and fixes. Challenge 1, division by 0 when the divisor is 0. The torch.dev function will result in a runtime error. Sample use case that resulted in challenge 1. Python. Import torch. A torch, tensor 1. 2. 3. B torch, tensor 0. 0. 0. C torch, diva. B. This will result in a runtime error. Fixes to challenge 1. Handle division by 0 by checking the divisor before performing the division. Use the torch where function to selectively apply division only where the divisor is non-zero. Replace the zero elements in the divisor with a small non-zero value to avoid division by 0. Challenge 2, integer division. When performing integer division, the torch.dev function returns the quotient with the flow function applied. This means that the result is rounded down to the nearest integer. Sample use case that resulted in challenge 2. Python. Import torch. A torch, tensor 5. 7. B torch, tensor 2. 3. C torch, diva. B. Rounding mode flow. This will result in 2. 2. Fixes to challenge 2. Use the rounding mode argument to specify different rounding modes. Available rounding modes include flow, trunk, seal, and round. Convert the input tensors to floating point types to perform floating point division and avoid rounding issues. Challenge 3 different data types. If the input tensors have different data types, the torch.dev function will convert both inputs to the data type of the first input. This can lead to unexpected results if the data types are not compatible. Sample use case that resulted in challenge 3. Python. Import torch. A torch, tensor 1. 2. 3. D type torch, float 32. B torch, tensor 2. 4. 6. D type torch.int 64. C torch, diva. B. This will perform the division as float 32. Fixes to challenge 3. Ensure both input tensors have the same data type before performing the division. Use the D-type argument to explicitly specify the desired data type for the output tensor. Torch, divide. Description: the torch, divide function performs element-wise division of two tensors. It offers different modes for handling division by 0 and supports broadcasting. Inputs. Input 1 AP torch tensor representing the dividend. Input 2 AP torch tensor representing the divisor. Outputs. Output 1 AP torch tensor containing the element-wise division results. Steps. Step 1 The function iterates through the elements of the input tensors, performing division on corresponding elements. Step 2 The output tensor is generated with the results of the division operation. Challenges and fixes. Challenge 1 Division by 0 if an element in the divisor tensor is 0. The result of the division is undefined. Sample use case that resulted in challenge 1 dividing a tensor by another tensor containing 0 values. Fixes to challenge 1. Use torch. Divide input 1. Input 2. Out N1. Rounding mode trunc. D-type none. Set the rounding mode parameter to trunc to truncate the result to the nearest integer. Use torch. Div input 1. Input 2. Out N1. Rounding mode trunc. This function will perform flow division, which rounds the result down to the nearest integer. Challenge 2 broadcasting. If the input tensors have different shapes, the function might need to broadcast them to match the dimensions for element-wise division. This can lead to unexpected behavior if the shapes are not compatible. Sample use case that resulted in challenge 2 performing division between tensors with inconsistent dimensions. Fixes to challenge 2. Use torch. Broadcast tensors input 1. Input 2 to manually broadcast the tensors before applying the division operation. Carefully check the shapes of the input tensors and ensure compatibility before applying the division operation.